¿Ya? Perfecto. Pues nada, pues lo primero, buenos días, muchas gracias por venir. Pues nada, vamos a ver una charla de Carlos Mariñas. Carlos Mariñas hizo la licenciatura de Físicas en la Universidad de Santiago de Compostela. Luego de allí pasó al IFCA, donde estuvo haciendo el doctorado. Y luego ahora mismo está contratado en Bonn y está colaborando en el Detector Belle II. De hecho, el año pasado estuvo de Technical Coordinator de Belle II más o menos y prácticamente se montó casi solito el detector. Y ahora mismo está de Rack Coordinator del experimento. Así que, pues nada, os dejo un poco, la charla va a salir en inglés y eso, espero que sea más entretenida seguro.
Vale, gracias. Okay, thank you very much. I'm going to make it in English, sorry. I don't know how to give talks in Spanish, unfortunately. So, thank you very much for the kind invitation, and of course it's a great pleasure for me being here, and also a great responsibility, actually, to talk about the phase 2 run of the Belle II experiment with specific focus on the pixel detector, results on the pixel detector for the phase 2 run. So this is the outline of the talk. It basically contains 3 different parts. First, I will give just a brief appetizer on the flavor of physics program that we want to do there. And then I will jump directly to explain a little bit how the accelerator works, and especially then the different parts that make the detector. So as you know, the high energy physics experiments can be divided or split into 3 different categories. The astroparticle physics experiments can be basically here in this kind of red dot, that is the cosmic frontier. And then if we go to, let's say, experiments that are working in man-made accelerators, those can be divided into additional frontiers. One, like the LHC, are here in the energy frontier, in this blue part here. So in the LHC, we go with moderate luminosities, but as high as possible center of mass energy. And contrary to that, the strategy that we follow in the Belle II experiment is try to search for new phenomena beyond standard model using medium energies, around 10 GeV or so, but as high as possible luminosities. And in this case, Belle II is basically here sitting in the intensity frontier. I don't want to convince you actually that what we do is right. So we basically go on with the success story that was initiated in the last century by the original B factories, Belle and Babar, that ran for more than a decade, as I said, in the last century. They recorded more than 1.5 Fibers-Autobahn of data, corresponding to roughly 10 to the 9 BB-bar pairs. And just to stress how important those experiments were, both were basically mentioned explicitly in the Nobel Prize that was awarded in 2008 to Kobayashi and Mascava. And this is a plot that basically shows that integrating luminosity always pays off. So here we have the integrated luminosity as a function of the year. And as soon as we were gathering more and more luminosity, we were making steady discoveries. So we don't want to reinvent the wheel, we will just go on with what worked already in the original Belle and Babar B factories. So just an appetizer, as I said, I'm not an expert so far, but what we plan to do in this new super flavor factory is to search for physics phenomena beyond the standard model, basically as everybody does. In our case, in B, D, and tau decays, and we want to do precision measurements on the CKM sector, and the studies are rare or forbidden or highly suppressed processes in the standard model. There are many potential new physics sources, but as I said, I won't go into any detail. I just want to say that in order to perform the physics program that we have in mind, we need 2 ingredients. First, it's a high luminosity accelerator. In our case, the machine is called SuperKEKB. And then we need a high resolution and large coverage detector that is capable of exploiting the high luminosity that comes from the accelerator. And in our case, the detector is called Belle II. So this is a sketch of the machine. So here on the left, we can see basically 3 different or distinctive parts. First, we have a linac, as always, a positron damping ring, and then the main ring. And we have a single interaction point, and this is where the Belle II detector is located. The machine is an asymmetric energy plus and minus collider working at the center of mass energy of the upsilon 4s. You will learn later on why exactly here. And the key figure, the figure of merit, if you want, of this machine is the high luminosity. We will reach around 10 to the 36. That is something like 40 times what KKB achieved, and that is currently the world record. Here you see the functionality, I mean the dependence on the functionality on the beam current, and it goes like 1 over the size of the colliding beams. So basically, in order to reach this luminosity, our approach is twofold. First, we put high current, 2 times more what we had in the old machine, and in particular, we will basically play with the sizes of the beams. We will be colliding what we call nanobeams. So this is a comparison between the beam, the colliding beam, the sizes in the old machine compared to the new machine, and the vertical size of the beams at the IP will be as thin as 50 nanometers. Here in this plot I show the integrated luminosity and the peak luminosity as a function of the year, and the commissioning of the machine and detector was done, or is being done, in 3 different phases. Phase 1 finished in 2016 already. This was the first time we managed to circulate electrons and positrons on the main ring. The second phase happened in spring this year. This is what the talk is about, actually. There we had the machine in the final configuration, and Belle II was, let's say, partially completed. So it was all done in a final shape, but the pixel detector and the strip detector were not complete yet. And then, starting from March 2019, next year, we will start with the full Belle detector also, and this is what we call the physics one, if you want. Our plan is to achieve the 50 inverse autobahn of data by the year 2025 around. So, as you can imagine, going from a B factory to a super B factory with 40 times more luminosity implies that we had to basically build a new machine almost from scratch. So we had to replace many of the components there, a lot of new magnets, but especially I would like to stress that here, close to the interaction point, this is where I'm mostly interested in. We have a new interaction region with a very thin, very light beam pipe, and we have a new final focusing system, some quadrupoles that are basically inserted inside Belle II, and those magnets make the nanobeams possible. So this is an aerial view of the Keck Lab. So this is where the machine is hosted. So Keck is, as you know, the high energy accelerator research organization in Japan. It's the national accelerator lab, if you want. It's located in Tsukuba in the Ibaraki prefecture, northeast of Tokyo, something like 40 minutes away or an hour or so by train. And it's near Mount Tsukuba. For those who are familiar with the Japanese culture, you know what that means. For us, it's basically just a mountain. So it's as important as Mount Fuji for them, actually. So here you can basically identify the 3 structures that I've mentioned before. So we have the linear accelerator, then the main ring where the SuperKEKB is actually located, and we have one single interaction point here. There is a hall where the Belle II detector is placed underground. We have other facilities like photon factories and so on, but I will not go into any detail here. So, as you can imagine, if we had to refurbish the machine, if now we go for 40 times more luminosity, there are also some implications on the detector side. In particular, we will have higher band rate. This is something that we want. This is why we build this thing. But there are some, caveats we have to cope with. So we will have more trigger rates, and we will have to adapt our DAC and computed requirements accordingly. But of course, this comes with a price that we will also suffer from higher backgrounds. That means we have to build more pixelated detectors and more rad-hard, and so on and so forth. So also some disadvantages here. So all in all, basically, we had to also upgrade the detector more or less entirely. And the new detector follows Belle, and it's called Belle II. So the Belle II detector is being built, or has been built by the Belle II collaboration. It's an international collaboration with more than 100 institutes, over 25 countries. So you see we have basically institutes all across the globe. And we have more than 850 researchers. So it's a medium-sized collaboration, if you want. It's more or less like LHCb or something like that. And in particular, in Spain, only Valencia, IFCA in Valencia is member of Belle II. And although IFCA is not a Belle II member, you know that you have participated substantially, let's say, with the monitoring system of the pixel detector and the SPD. So I will come a little bit more with some details later in the talk. So concerning the Belle II detector, compared to the old Belle experiments, we have several areas that we will make it better. In particular, a light in the detector, precise vertex signal tracking system, efficient particle identification, high resolution electromagnetic calorimeter, then some muon ID, and of course some adapted, as I said, DAQ. So this is also a medium-sized detector, so it's something like 10 by 10 meters, something like that. And you have here a comparison for knowing the scale. Going a little bit more into detail, so this is a cross-section. Electrons are coming from the left, positrons from the right. They collide here at the center. Oops. Okay. No.
No more.
It's coming good. Okay, so yeah, electrons are smashed against positrons here at the IP. The first detector the particles created will see is the vertex detector. I will come to this point later. Then we have a large gaseous volume with a drift chamber. Then particle identification in the barrel and the forward regions. Then some electromagnetic calorimeter, a 1.5 Tesla solenoid field, and then a muon detector surrounding. So as I said, in order to understand a bit better the role of the vertex detector, I will try to explain what's the typical event looking like in this facility. So we collide electrons and positrons at this particular energy. Therefore, we hit the upsilon Ferenc resonance, that is a BB bar bound state, and then this upsilon Ferenc decays 100% of the time in BB bar pairs. And then, of course, this further decay. So it's an asymmetric collider, so there is a boost in the forward region, the particles will tend to fly forward, and the role of the vertex detector is to determine precisely the decay points where these primary, secondary, and tertiary vertices are located. And in this case, basically we are talking about typical distances of something like 100 microns, something like that. So we need precise vertexing for reconstructing these decay vertices. That means we need a high resolution, and especially, this is very important in our machine, we need a light in the detector system. In our case, the vertex detector is a 6-layer silicon detector composed of 2 ingredients. So this is a CAT model of the phase 3, the final vertex detector that we call VXD. Very close to the interaction point, we have a 2-layer pixel detector that is implemented using depth-fed pixels. And then surrounding the PXD, we have a 4-layer double-sided silicon strip detector that is called SBD. So as I said, we have strips over there. Concerning a little bit the requirements and parameters, especially on the PXD part, so I will also come to this point later. So the expected radiation was not as hard as Atlas or CMS, but we expected something like 2 megarad per year. After phase 2, we have updated numbers actually, and this will be more like 10 per year or so. So in the end, we are in the ballpark of 100 megarats or so. And this is actually worrisome at the moment. We are reading the 8 megapixel pixel detector every 20 microseconds in rolling shutter mode. And this is actually the point here. So in our case, the particles in the final state have very low momentum. So as low as a few tenths of MeVs. And basically that means we are limited by multiple scattering, and the key figure here is the material budget. So we have to be very thin, extremely thin. The pixel size doesn't matter too much, because we are limited by multiple scattering in the beam pipe already, but we have to make it very thin. In our case, the maximum tolerated is 0.2 radiation lengths per layer, and for those who are not very familiar with these numbers, 0.2% of X0 is the equivalent to 100 microns of silicon or so. And this includes everything. So the sensor, ASIC, support structure, cables, whatever. It has to be inside of this 100 microns equivalent of silicon. So that means, this is our nightmare, auto-transparent detectors, but also lightweight mechanics and basically no services in the acceptance. This is a depth-fed ladder. This is the basic unit of a depth-fed based pixel detector. So by the repetition of this unit in this cylindrical arrangement around the beam pipe, this is how the PXD is implemented. We have 3 different regions in this ladder. Here in the center, this is where the sensor this is the active area if you want. This is where the depth feds are grown here. Then in this balcony we have the first type of ASIC that is called switcher. With this chip we can choose which region of the matrix do we want to read. And we read this in rolling shutter mode, so we go row by row. And then at both sides of the ladder we have 2 different flavor ASICs. First is the DCD, it's the analog front end. Basically here we have ADCs to digitize the drain current of the transistors that we have in the sensitive area. And then we have the DHP, that is the first data compression stage if you want. So basically this chip performs combo mode correction, pedestal subtraction, zero suppression, and this chip is also in charge of the timing and the trigger control, and basically decides what happens in the ladder itself. Okay, concerning the off-module signal flow, so each of the module is connected to the outside world. The back-end electronics, I won't go into detail. So we have some DAC system that is called the Highenergy. What I'm interested mostly in is what happens in between. So here you build a very thin, very light, as I said, 100 microns equivalent detector, and then you have to put a lot of Kapton and cables and patch panels and PCB and whatever. And actually for us, in the instrumentation part, this is actually the tricky part, because you will see later on a picture of this beautiful structure, but then if you add this thing on top, you have something like this. And this is actually the worst nightmare you can imagine. Okay, so this is where you make mistakes. And this is only with 50% of the pixel detector included. So you have to add, another time more or less something on top. So this is just to say, since you are also involved, you know this very well, in the development of mechanics and structures for the new colliders, we have to take this into account from the very beginning, from the point we start thinking how to build a detector. Keep in mind that you have lots of services to route. Yes, okay. Increasing complexity. I just want to say that in the end we reached this level of maturity, but actually it took us something like 10 years or so to reach this point. So we started with something that we call hybrid 4. Even S3B, I started working in the project with a hybrid 3 that was even the father of this one. And basically this is a path starting to test small matrices only, adding one flavor of each ASIC at a time. Then you go to multi-chip mode operation, then you try to understand the electrical properties of the module. So basically this is a 10 years work. This is something we should also keep in mind for future experiments. But in the end, okay, if you're lucky, you build a beauty like this. And this is one of the ladders that I showed before. So this is a single piece of silicon. Everything is silicon, it's a monolithic thing. Here we have, in this ladder, more or less 500,000 pixels. The thing is thinned down to 75 microns. It's roughly half of the human hair, the thickness of a human hair. and we have this pixel pitch. And then you see we have all the ASICs that I've mentioned before, some wire bonds connecting to a capton, and then we have this mess of cable somewhere. Okay, at some point, as I said, after 10 years, we reached this level of maturity, if you want, and basically the focus of the project changed completely. So we were no longer interested in, you know, how the ASICs work, or, you know, how to put a source and calibrate the sensor. The thing moved a bit more from module characterization to building a complete detector system. And this is something that happened a few years ago in a setup that we call Percy, that stands for Permanently Running System. And basically we put there the phase 2 PXD, if you want, and we started to develop or to finalize the back end and the monitoring system, the slow control, you know, all the software and the DAQ part. And I put especially this picture, not because I'm there, you know, fixing the screw, but you can basically see here that from the very beginning, from the early stage of this project, there was already a contribution from you. And actually this was highly appreciated. It was basically running from the very beginning. And this helped a lot in the commissioning, because we had always the temperature and the humidity in this volume under control. So we could operate the sensors basically safely. Just to show a little bit more, again, so we have this beauty here, and then we have a hell of a mess of cable somewhere. And basically in this permanently running system, it was a tool for integration. We tested the complete 2 Vertex detector in Europe before we shipped the entire thing to Japan. So basically we disconnected all the cables, we put everything into a container, and this was shipped on a jumbo directly to Narita in Tokyo. Great. Now let me stress a little bit what we did in phase 2. So this, I will be mostly showing results from this part here. So as I said, phase 2 started in February 2018. It ran until the summer break, mid of July this year. And we operated for the first time the accelerator in the final shape. So we had also the quark magnets inside of Belle II. It was the first time we operated the machine with focus beams, and we had the first collisions. From the Belle II side, from the detector side, Belle II was complete, but the Vertex detector. Instead of these, we had a small sector of PXD and SBD, as I will show later on. So this is again a CAD model of the final VXD. This is what we call phase 3 VXD. But in phase 2, this volume looked like something like this. So this is also what we call the Beast experiment. So this is probably the best logo ever. So we had a small sector of PXD and SBD in the horizontal plane. And the rest of the volume was basically filled with dedicated radiation monitors. So also IFCA contributed in the monitoring system of one of these Beast detectors that we developed in Bonn. The goal for this experiment was to help in machine commissioning, basically tell the accelerator guys, yeah, the backgrounds are too high, you have to do something. We didn't want to damage the final detector, so this is why we went for this option. And of course, we wanted to ensure doing real measurements with the real detectors in the end, although in just only a small sector in the horizontal plane, that it was safe to install the final thing. And this is a picture of the phase 2 PXD. This is in Japan after this the shipment from Europe to Germany, from Germany to Japan. And this is after attaching the PXD to the final beam pipe. So here in the center, I mean, in the end, we removed these bars here. This is the real beam pipe, so it's a thin 200 microns beryllium pipe. The modules arrived in September. Then it took us something like a couple of months or so to put things together. And then after we verified everything was fine, we pushed the thing in Belle in November. So again, this is what David was referring to. Yeah, it took me 2 months to connect all the things, but finally it worked. And again, you see that those are the fibers. Also the bit was there. And after final detector verification in the clean room, that everything was basically working, we closed the volume, we took the crane, as simple as that, and there was a Japanese operator very careful transporting this thing. The assembly flew across the hall, and then basically you just push the thing in by hand, and that's it. Yes, finally, after we did all that, there was a period for machine commissioning, but finally on the 26th of April this year, we saw the first collision. We were all very happy. The beams were not very small, but this was not the purpose. The luminosity was still very, very low as well, but basically we saw the first event. This is something like QQ bar background probably. But we were happy, and this was the scene in the control room. Yeah, I was there also as run coordinator with Tom Browder. This is the spokesperson of the collaboration, and this is Ryosuke Ito-san. This is the head of the DAC system. And we were basically all very happy. So, concerning phase 2 results, phase 2 was over 17th of July this year. The target here was twofold. First, a verification of the nanobeam scheme from the machine point of view, and achieve a luminosity that was more or less 10 to the 34. This is what KEKB achieved at the end of the day after 10 years of operation. So it was quite challenging actually. We had 2 months for achieving this. But in the end we managed. So as I said, we reached 10 to 34 levels, twofold. First putting current in the machine. So this is an evolution of the HER and LER current, and this is luminosity. It's a function of time. So we were steadily increasing the current we put in. At the end we reached 800 milliamps in both rings. And with this, together with going down, squeezing the size of the beams at the IP, going down in beta star y, basically at the end we reached beta star y 3 millimeters. That is the equivalent of size of the colliding beams of around 300 nanometers. Basically we reached 5.5 times 10 to 33. So basically this was successful from the accelerator point of view, and then in these 2 months of operation we integrated something like 500 inverse picobarn of data in Belle. Of course, with early physics, the physics colleagues were very excited, but actually for me it was a way of understanding the performance of the detector. So we basically spent the first months of operation trying to reconstruct or rediscover particles that we know they are there, and those were useful to understand if the detector was working nicely or not. So of course we saw some B's and J psi's and pi zeros and K shorts and lambdas and all that. So in principle everything was working nicely. As I said, I was in charge of the integration and commissioning of the Vertex detector, so I was especially interested in watching the performance of the PXD especially. And this is the performance on the very last day of phase 2. So here we have the pedestals of the modules, and this is the noise. So the pedestals were, very nice actually. They were very compressed. We had lots of room for signal. And also concerning the noise, it was pretty homogeneous, and the equivalent, the peak is something like 100 electrons equivalent noise charge. So the detector works also nicely. Concerning signal to noise, we divided, so the numbers you see here are the signal to noise ratio for 6 times 4 segments in a module. We had signal to noise ratio everywhere above 50 with more or less 10-15% spread. And this is the Landau that we saw on the 4 modules. So you see nice Landau distributions here. Signal to noise, as I said, above 50. And you also see a particular figure here, or feature if you want. Especially on the inner detector modules, we saw this kind of Gaussian peak. First of all, we thought, okay, this is noise, but it's not noise. The threshold was set to 900 electrons, but it's somewhere here. And this peak is actually coming from 10 keV synchrotron radiation photons. So we were also sensitive to these low soft synchrotron radiation photons as well. Concerning efficiency and resolution, so you see this is a resolution. If we include CDC, the drift chamber, and the strips only, so it's quite broad. This is with only 2 inverse picobarn of data. But if you include the PXD, then basically your distribution narrows down, and we are more or less in the ballpark that we expected. So we expect something like 12 microns or so. This number can vary depending on your track selection. If you are more strict, then this number goes down, of course. Anyway, this is just to say that the PXD was successfully incorporated into the DAQ stream, and basically we could see events together with the rest of the detectors. And this is an evolution of the efficiency as a function of the time. So this is a function of the run number. And this is between 60% and 100%. And this is a thing. So as you see, actually the efficiency of the pixel detector varied along the runs. And well, we might ask ourselves why, especially why do we see these drops here? In the end, after some adaptive biasing, we reach efficiency that is in the 98%, 99%. As I said, depends a bit on how tough you are with your cuts. So it's acceptable. It's not brilliant, but it's, well, sufficiently good. But basically what you see here, something I want to stress, the efficiency in particular, the charge collection properties of the sensor, depends heavily on the voltages. So if there is no optimization of the voltage, typically your efficiency suffers. So this is what we saw, for example, in these periods. These drops down here, this is due to radiation damage. So basically we integrated the first half a megarad to a megarad TID, and that basically means you have to adapt your gate voltage in order to make the channel conductive again. So if you don't do that, we didn't do this on a daily basis. So basically your signal to noise degrades, your GQ degrades, and then your efficiency goes down. This is something that we have also measured in test beam campaigns, and basically this was as expected. So after all, we took some time for optimizing these voltages, and then as I said, at the end of the day, it was pretty much okay. And I want to, explain a little bit, why do we have to optimize these voltages, in particular the drift and the backplane. So here, this is efficiency. Just have a look at the cluster charge. Don't pay attention to the rest. So this is the layout of a pixel, of a depth-fed pixel. Here, actually, we don't have one pixel. We have 4 pixels. So this is one pixel structure. There is a drain, there is a gate, and there is a source. And this source is shared between this pixel and this pixel. So just have a look at this, okay, at this block here. And this is what we have here, okay? So basically what we have is the electrons have to make it to a very tiny place, that is what we call the internal gate. That is somewhere here, is this tiny red dot there. The scaling of the pixel size is done via additional implantations that are called drift. So as you can imagine, if you have a particle that creates signal electrons here at the very edge, if your drift potential is not really applied in a way that you push the electrons in the internal gate, those might be lost. And this is what happens actually. So this is the cluster charge. This is for perpendicular incident MIPS. If you hit the internal gate, then you collect all the charge. If you don't apply the right voltages, if you hit a corner, then this charge is lost. And this you see as an efficiency drop. Contrary to that, and this is what we see, the efficiency is in the 90%, 94%. If you do the right thing and you apply the right high voltage and drift, then you don't see this structure anymore. So your detector basically collects charges homogeneously, and then you recover this efficiency that is lost, in this case, in the corner of the pixels. So this is just an example with test beam data. And as I said, this is due to radiation, TID. Okay, on the not so bright side, so PXD was fine, Belle II was acceptable. On the not so bright were the beam backgrounds. So we wanted to study the backgrounds during this phase with this BEAST experiment and also the entire Belle. We had a number of big beam backgrounds contributing. So in intra-beam scattering, synchronous radiation, blah, blah, blah. I will not go into details. And as I said, in the end, we didn't manage to actually understand the different contributions from all. The machine is a very complex thing, and it's very hard to have all the parameters under control. So what we saw, for example, is this is related to the point I've mentioned before. So using Monte Carlo simulations, SAT, Gen 4 stuff, we basically thought that we were accumulating 1.8 to 2 megarad per year in the PXD. But in the Monte Carlo, you never account for things like that. That can also happen. So it was the first time we switched on the machine. What we see here are the vertex reconstruction, the V0s using Belle. overlaid to the blueprints of the beam pipe. Okay? So this is the cross-section, electrons are coming like this, and positrons are coming like this. And this is the IP, this is 0, 0. And this is where the PXD is located, here, right? So what you see is actually, you are, of course, seeing particles from the IP somehow, but you are seeing particles everywhere. So this was unexpected. In particular, we had some hotspot here. This is the Venus. This is the connection of the central beam pipe to the machine somewhere, and the same thing here. So there was something clearly wrong. And we, using Belle, we actually saw that the IP, it's hard to see here, but the IP was not at 0, 0. We were not colliding particles at the origin. We were colliding particles 1 centimeter downstream. So there was something very wrong with the orbit on the machine. We were hitting heavy metal structures somewhere outside, and we were colliding particles really off of what we expected. And until we found out that this was the case, we accumulated maybe, some dose on the PXD, and this was never, accounted for. So this all sums up. Then, of course, we found these, we talked to the machine, they corrected the orbits, then everything went to 0, 0, and then basically what you see is nothing, everything is clean, everything is coming from the IP. But it took us a few days until we realized that, there was something wrong. So my lesson is be careful with the background estimation and always, add some headroom to your calculations. Also, another thing, this was very interesting. Maybe nobody of you have ever seen the effect of a ½ amp electron beam over a collimator. So we basically tried to cut down the tails of the beam, and we went a bit too far down. So basically what we see is that the beam went through the collimator. So this is basically, the beam went like a knife on butter. And this is on one side. We had an accident with another collimator as well. We basically scratched the tungsten coating of the collimator. So it was not as severe as this one, but you see actually the beam tails scratched the surface of the collimator. So this is another lesson. Be careful, and do tune in with small currents also. Here also you see that actually it's damage in the perpendicular direction. Probably this is due to, I don't know, there was so much heat transferred that it was just, the material just cracked somehow. Another thing, beam tails. This is a cross-section of the central beam pipe. This is the positrons are going in this direction to the blackboard. And this is 22 centimeters away downstream from the IP. So what you see here, this is again Vertex reconstructed using Belle. So what we see is there should be nothing here. The beam should just go straight. But we were actually creating showers of particles in the horizontal plane at both sides of the beam pipe. So that means we had long tails that were actually touching in the horizontal plane the inner surface of the beam pipe, and we were again showering into the Belle II detector. So also beam tails were really never considered or taken into account in our calculations. So it was a hell of a mess, and this was just an example. We had storms and dust and ghosts, many things that well, I could use another hour to explain what we had. But it's a new machine, plenty of new features. We understand some of them, but not all. So we will devote also a few months at the beginning of phase 3 to understand a little bit better how the machine works. This is just an example. For no reason, from time to time, there was a beam dust event. So we basically burned some impurity, some particle of dust in the inner side of the beam pipe. This changed completely the vacuum in the machine, and then we saw basically the entire Belle II detector was glowing. And this is one of these events on the PXD side. So PXD typically should see an occupancy of 0.5%, and from time to time we basically had even 50, 60% or so. So this happened from time to time. Okay, so far for phase 2, and now I'm coming to just the last part, some nice pictures. What is still ahead of us is phase 3. So phase 3 is the physics run. As I said, we expect the first beams to come on March 11th, and we will have the final detector and the final accelerator in the final shape. And the goal would be to steadily increase the luminosity. So how do we plan to do that? Of course, put more current. In phase 2, we reach 800 milliamps. We have to go to 3.6 amps in the end. And we are still a long way to go in squeezing the beam sizes. So also 1 order of magnitude to go down. So this is the beta star y, the size of the beam, if you want, at the IP as a function of the year. We started here, we went down like this. This was the end of phase 2, but still we have a long way to go actually, and this is quite tricky. And this is something we have to do in the next few years. As I said, in phase 2 we had a small sector of PXD and SVD, and we wanted to have the final thing for phase 3 starting in 2019. Unfortunately, there was a problem with the production of the PXD. We had lots of issues in the gluing process of these 2 modules. So a ladder, something I didn't mention before, a ladder is built out of 2 modules glued here at the center. There were a lot of issues in gluing and particle contamination. We lost a lot of modules, and we decided to basically stop the gluing and to go for a 50% PXD for the first 2 years of operation. We didn't have enough modules left for trying. I can give all the details how this happened, but this was very unfortunate. So for the moment, in 2008 until the summer shutdown in 2020, we will go for what we call now de-scope PXD. So we only have, as I said, 50% of the modules in the end in this configuration. So layer 1 is complete, so this part is complete, and then we have 2 additional ladders on layer 2. Anyway, this was installed in Japan, and we put also the SVD around, and this is SVD is complete. It's actually quite beautiful. I mean, if you don't, you forget the fact that there are some ladders missing there, actually it's a very beautiful picture. And even in phase 3, in the commissioning in the clean room, we managed to see some cosmic going across SVD and PXD. So this happened in September and October this year, and what happened actually last week, we basically again closed the volume, same as we did in phase 2, now with the final thing, and then we pushed the thing in. And what we are doing right now is basically cabling these cables that come from the inner volume to the dock boxes that are connecting then to the back-end electronics on top of it. And this is what we are doing right now. So, this brings me to the summary. Belle II will search for new physics at the intensity frontier, complementing the LHC, and our target luminosity is 50 inverse autobarn. Phase 2 experience with the PXD, it worked nicely. The performance was verified under realistic conditions. The backgrounds, as I said, were significantly higher than expected, and we should keep an eye open to this. Concerning phase 3, the VXD is installed. We are doing cabling and sanity checks right now in Japan. We had some ladder gluing problems, so we installed this 50%, and we started preparations for a complete replacement of the PXD by the summer shutdown in 2020. There will be a big shutdown in 2020. We have to also do some work on the particle identification device in the viral region, so we will use this time for fixing both problems. And we are expecting physics data, phase 3 starting mid of March 2019. So thank you very much.